it's my pleasure to introduce Dr. Lake. I was at UT Austin, graduated from UT, and worked with Tom Edgar, one of his collaborators there at UT Austin. And between him and Leon Lasden and Tom Edgar, they've produced an impressive body of work. And so Dr. Lake, he is in the Department of Petroleum and Geosystems Engineering at UT Austin. He has his undergraduate degree from Arizona State University. So the other university that also is the Fulton College of Engineering, okay, the other one in the U.S. And then Rice University for his PhD. He is the author or co-author of more than 100 technical papers, 4 textbooks, and the editor of 3 bound volumes. He served on the board of directors for Society of Petroleum Engineers, won the '96 Anthony F. Lucas Gold Medal of the AIME. And he was also got the De Goyer Distinguished Service Award in 2002. He's been a member of the National Academy of Engineering since 1997. And just from those who work in this area know the impact of Dr. Lake's service in both from the professional societies, but also in his research and the influence that he's had in this area. So with that, I'd like to welcome Dr. Lake, and please join me in welcoming him.
It's funny how things come back on itself. At Arizona State, we played Brigham Young in football every year, and every year we figured we could beat those guys, and every year we lost. And now I'm at the University of Texas, where we play Brigham Young in football. Well, you can see where this is going. I'm delighted to be here. The hospitality's been really good. I'm going to talk about a topic which I hope is of interest to you, and I hope actually has some practical utility. It fits in the grand scheme of something called big data. How many of you here have ever heard of big data? Okay, how many of you have research projects in big data? Okay, now I think what I'm doing here may be not really big data, but it's bigger data, okay? And this falls under this little publication edited by Hay and Tansey. This falls into the 4th paradigm of engineering, which is, historically speaking, the first phase of engineering was empirical. This is before computers and before calculation. This actually probably goes back to the Middle Ages. The second paradigm is analytical. This goes back to the start of the previous century for people doing analytical solutions. We still do this. In fact, these phases have not really gone away. It's just it's been added to it by other things. And then the 3rd phase was numerical. So who can tell me when the first numerical simulation paper was written in the Society of Petroleum Engineers literature? I gave that to a yes.
1956.
Good, you were paying attention. 1956. And we are still in this phase here, but the betting here, and the thrust of that article there is that we are entering into a 4th phase, so-called data-intensive phase, big data. So I'd like to talk to you about our efforts, and it's going to be phrased not so broadly as big data. It's going to be phrased in terms of specific technology that we've been working on for some time. And the title is there. The right picture is the tower at the University of Texas. And the date is 2005, when we won a national championship in football. Those were the days. University of Texas, I have a slide on this, but I couldn't find it. It's a school of 51,000 people located in Austin, Texas. We have, in our Petroleum and Geosystems Engineering Department, which is different than chemical engineering and different than geology, We have about 600 undergraduates, about 200 graduate students, and 18 faculty. Now, if the oil price keeps falling as it is, that number will probably go down to about 150 by Monday. And so the title is Reservoir Characterization from Production and Injection Fluctuations. And it is a long-standing project. So those of you industry guys in the audience, how long have you been on a project for 20 years? Raise your hand. Okay. Do we have a point or something? Ah, there it is. Okay. So the first student was Belkis Refungil. This actually was a Latin American project down to right about here. He came from the Latin American country of Saudi Arabia. And then there is China, there is Iran, who's now at Chevron. And wow, look at that, an American snuck in here. And not only is he an American, he's one of your alums. Dan Weber is a chemical engineering graduate, I guess about 2004 or something like that. And so you can see the rest of them. And all of them have contributed quite a bit to the project, each one their own special way. So not only is it a 20-year project, it's 15 different students, including one who has to have the longest name in the record. That poor child, that name was longer than she was tall. And here are the current folks that are working on it right now. Tom Edgar has been a long-time collaborator of mine, and his name was just mentioned a few minutes ago. And so was Leon Lass. So, in case you don't know, oil provides about 80% of the transportation fuel in the U.S. And that's about divided equally between gasoline and jet fuel. About 1/2 of U.S. oil is produced by water flooding. I'm not sure I'm right about this, so if anybody has a correction to the statistic, I'd like to know. It just feels like that this is correct. All reservoirs are buried in porous rock. Okay, there's a fair number of oil company managers. I wonder if they catch this message. Once a barrel of oil goes into a well, there is no way to know where it will go. Really. That despite the fact that there are current methods for tracking it. They are expensive, time-consuming, and fundamentally inaccurate. Despite, in addition to that, periodic well rates are the most plentiful data type, often the only data available. Here's the way this project got started. One of the more significant achievements of my professional career was about 25 years ago when I entered into an agreement with a local consulting firm. And there I talked to several of their clients. They had usually come into possession of an oil field, a legacy field, if you will. And the conversation would go like this. Yeah, we can do something for you. Could you show me your seismic data? Blank, look. Okay, no seismic data. How about your well log data? Oh, yeah, we've got lots of well logs. They're in a warehouse up in Tulsa, and they're 50 years old. The logs. How about cores? Yeah, we got some cores. They're in another warehouse in Tulsa, but we're not quite sure where they are. And so, well, do you have well rate data? Oh, yeah, lots of well rate data. Sometimes 50 years of well rate data. So I racked my brain as to what exactly someone could do for a client who had only well rate data. Now, I'll back away from this a little bit as we talk. But at least it started off with, what can we do with folks that have only well rate data? A lot of well rate data. Okay, which would you prefer? A little bit of very good data or a lot of not so very good data?
A little bit.
We discussed that today too. What is it? Come on, guys.
Good data.
Good data.
Bottom line.
A little bit of very good data, or a lot of kind of not so good data?
Not so good.
What?
Really good data.
You would like to have a lot of really good data. In almost every case, you will pick the second option, a lot of so-so data. And that's where we are here. In addition, the technology started, and it's much like a time today in an era when the price of oil was low. Not too many people wanted to spend much money. So I'm looking for a technology that uses well rate data, doesn't cost the client very much money, and still is useful. Those rates always vary with time. That's a key thing. All scientific research must have a hypothesis. There we are. Here's the crux of the idea. You chemical engineers have had at least one class in which they talked, at least in passing, by control volumes, right? Didn't they? About control volumes. That control volume idea is an extremely powerful idea, much more powerful than is usually acknowledged in class. Because the control volume, you don't even have to know where it is. Right? You certainly don't have to know what it is. The geometry is completely irrelevant. Okay, and so we'll start with the control volume that, just for the sake of illustration, we'll do that in showing the upper right-hand corner there. And we have a time-varying injection rate and a time-varying production rate. And unless I say otherwise, the time-varying production rate will be both oil plus water, the sum of the two. This, of course, will be a reservoir here. And one can do a material balance, actually something called a continuity equation. Okay, raise your hand if you remember the continuity equation. Okay, what is it, page 60 on Vertica? One could write a material balance of oil, gas, and water, and you'll come up with this equation here, which says that the change in average pressure, which is there, multiplied times the compressibility pore volume, is going to be equal to the deficiency between injection and production. With a closure relationship, this is a petroleum engineering version of Newton's law, okay, a fixed law. One can relate the flow rate to the average pressure, something called a productivity index, and I will take that and I will substitute it in here. I'll get that differential equation, ordinary differential equation. The parameters change a little bit when we start talking about this space. In the normal petroleum engineering space, we're talking about permeability and porosity. But here we'll start talking about productivity indexes and something called the time constant, which is here. It's the total compressibility times the pore volume divided by the productivity index, and it will have units of time. And I know you immediately recognize that as an equation which had an analytic solution. I always say that in front of industrial audiences. I say, like, this is an equation of a type that you confront every day, which of course is totally bogus. Nobody in industry remembers ever seeing the differential equation. But here you can. So this says that this equation predicts that the rate at a certain time is equal to a rate at a previous time. And this can be attributed to a primary production phase. We're talking about water flooding here, but oftentimes there is a primary component to a response because of the injection, mitigated by the compressibility, and then this term here, which is the bottom hole pressure terms over here. So when the rate changes, it changes because the injection rate changes, or it changes because the bottom hole pressure changes. Now, when you go on bottom hole pressure, you know what I'm talking about? It's the pressure at the bottom of the producing well. Okay. So, that's the idea. We cut a lot of corners. Okay, we cut a lot of corners. It is nevertheless a physical model. what we'll do is adopt the history matching procedure. Okay, come on. It's, in a sense, it's pretty old. Because in the 1940s, people actually built electrical resistor networks to model flow-through porous media. Here's a photograph from a paper that was written in 1942. Here's a photograph of the actual resistor network. Yes, they did wire these things together for the purposes of predicting what would happen in the reservoir. If I let you dwell on the right-hand side of the figure, you can see they did a pretty good job. And the only difference between what we're doing here and what they did then is that we're solving the equations now rather than building something that solves the equations. So it works. Excuse me, keep pushing the wrong button. It works something like this. There's one injector and one producer. On the left is a plot that shows square injection rate and a plot that shows production rate, the green dots. And we just change the parameters of the problem until they match. Classic history matching. The model is so simple that you can do it in a fairly simple optimizer. And you can do it if the problem is not too complicated in the solver in Excel. We use cans. Okay. It's just history matching. Just history matching with a very simple model. Now, I have to stop here and say something which is an editorial comment. Those of you that are engaged in constructing large-scale models, millions of cells models, which is the industry norm right now, you should realize what a handicap you've laid on yourself in terms of operational flexibility. For one thing, history matching a model like that is extremely difficult. It usually takes months to do it. And for another thing, there's not much you can do with it once you have it. Usually you write a note to your boss to say, I've finished the history match. Okay? So I've deliberately gone in the direction of a simpler model. You can define the control volume to be the whole reservoir. You can define the control volume to be a volume around a producer. And remember, you don't even know, don't have to know what the geometry of the control volume is. It's just something that you nebulously use to write your material balances around. And so here the control volume is around a producer, and each one of those injectors is an injection rate, for example, I2 times a F2J, which F2J represents the fraction of the injected water that's going to that producer. So we'll let the data determine the control volume, and that determination will be done through these so-called interwell connectivity or gains. The fraction of the injected water that's going to the producer. We can even do it with something called CRM IP. Basically, we can let there be slices between injectors and producers. Just defining the control volume and make a fairly small change here in the equation. But they're all easy to history match. And this one is a little bit problematical because it has a lot of additional parameters to determine. So it's this one that we'll use the most. By the way, you notice I don't have the bottom hole pressure term in it because most legacy assets do not have bottom hole pressure. Who knows here? When I say legacy asset, you know what I'm talking about? An oil field that was sold from one company to the next, to the next, to the next. By the time you get to the third company, it certainly is a legacy, but they've lost the data. Okay. So unless I say otherwise, the bottom hole pressure term will not be there. Like equations. I'm going to pause and see if you have any questions. Yes?
So if your IJs, why do you have that relation? Because I feel like that could be added up to the any number.
Well, you have to add up to the production.
But it could be any portion from any of those injectors.
Oh, it certainly could. In fact, that's what we will determine. Other questions? Yes?
What are the assumptions involved in this kind of an analysis?
Lots of assumptions. Compressibility is constant. Pore volume doesn't change with time. The productivity formula is for semi-steady state only. And sometimes it's not. That's just the start. There's probably some geologic assumptions associated with it. I don't care. Let's go. Let's just do it. Okay? Lots of assumptions. Are we good? Other questions? Okay, I loaded in a few more equations later on, but I want to talk a lot about some results. So, of course, it is a minimization, and here is the objective function, the actual rate versus the model rate squared. We talked about objective function earlier today. I think there are other things that you could do here. For example, on objectives, some of which might perform better than what we do. And I'd like to point out to you that there's a sum here over all producers. So when we do this, we optimize the whole field, not doing just one well. One of Dan Weber's contributions was he used the single well optimization. It's what he called a warm start. He got that term from you. It's what he called a warm start to provide a starting point for the global optimization. But we're doing the whole field. And that's kind of written a little bit more. We have to determine a fitting window because we are using time here as the rule of the random variable in a regression model. So here's the optimization over the number of producers and the number of the fitting window. The model parameters are here. The one we'll use the most is the CRMP, which contains the connectivities, Fij, and tau, the time constant. I have a lot of trouble explaining time constants to most audience because the chemical engineering-based audience is probably old hat, right? So it's the same thing, except we're using compressibility. You will also see some R-squared plots, which give you the measure of fit. Some odd things in these R-squared plots, but we'll talk about when it shows up. It's just 1 minus the scatter removed by the model divided by the scattered about a mean. So that's the equation. Okay, here we go. First case, southwest level field. This is in Weber's dissertation. Here's the plot of R-squared values, one for each producer. Come on, guys.
Yeah, we're okay. Go ahead.
Okay. Can't you kick out some of these students? So there's the producer number across the bottom of it. And you can see the R-squared values here are about 0.6 for each producer on average. There are, to be sure, some losers, right? Aren't very good. And there's some odd behavior here, but this is because we're actually doing global fits and we're plotting individual well statistics, so it's not anything to be concerned about. But an average R-squared of 0.6 is pretty darn good. It satisfies what I will call Lake's law of petrophysics, which is to say we kill for 0.6. And of course, those of you that study petrophysics know what I'm talking about, right? And this has been a persistent feature of all of our fitting. As simple as that model is, there's enough degrees of freedom in it not to make the fits just super. There's a plot of the gains. Remember, these are the connectivities. This is for southwest leveling. 250 producers, 150 injectors. We're doing the whole field. We're only showing the gains between injectors and producers that are greater than 0.5. Greater than 0.4. Greater than 0.3. Of course, as we lower the limit, the reservoir connects up better, right? 0.2. Okay, now I'm going to pause here, because if this reservoir behaved as the textbook says it should, and I wrote some of those textbooks, if this were a 5-spot, the connection should be 0.25 everywhere. They aren't. And this honestly drives people crazy. And they say, well, that's not what the books say, or that's not, I've never seen a water flow performed like that. And I say to you, you ever heard of geology? Because these connections are governed by the geology. They're not governed by where the wells are. In fact, when the wells were first drilled, operators scarcely gave a thought to what the geology was. So, very important. This is the geologic model for the technology. It's the output. It's not the input. It's the output. It's not the input. Now I'll leave it to other folks to decide whether this is a fluvial bad take, whether that right there is a good area for infill drilling, or whether it makes sense at all to have these connections at such a great distance. That usually bothers folks. So how can you have wells connected that are such a long ways away, particularly if there's a well intervening there? And the answer is, just go to the field and look at some data. These tracer tests almost always show about 50% of the tracers just disappearing, and the other 50% showing at wells at locations that you did not expect. So I've gotten over being bothered by this. Fits. Individual wells. Well, 184, 127, well, 74, which we call a poor fit. Not so poor. Well, 201, which we call a poor fit. Not so poor. Well, 210, which were wells that are a great distance apart. Well, 103, which was skipped over. These are history matches by well. Okay, I defy you to find a large-scale simulation that does history matches by well in a large field. But we've done it, and it is a little non-intuitive. Okay, I'm pausing. Any questions? Yeah.
Well, some of those injector wells that weren't linked to the producer wells, are those candidate injection wells that shut down? They're not necessarily producing. Is that what the gain is?
Yes, I'll show you that in just a second. Okay. Other questions? Yes.
Yeah. So let's say a company started to kind of pick up their game. They started to record all the types of data you mentioned earlier, getting the core, everything. How many years would it take them for that to be worth it? I mean, would that be better than this by much?
Well, of course it would be better because it's additional data. And the more data, the better. But we can do this in an afternoon. So it's always a balance between effort and benefit. Other question? Yes.
When you have some poor fit for producer, what's the meaning of?
I cannot understand. Can somebody tell me what she said?
When you have some poor fit for this producer, for example, you don't have some good fit for some data.
For the producer.
Those are about as bad as they get.
When you have some poor fit, what's the meaning of that? You cannot use CRM for that producer. Then we don't have good.
You mean if it's a poor fit, we can't use it?
Yes.
I suppose so, but you could say that about any simulation. fact, I see this all the time, is it seems to be people want to hold this technology to a higher standard than they do to simulations with CRM. Your question. I'm going to turn it around and I'm going to sum up the gains over the producers and subtract this from 1. Now, if all of the fluid is being counted for by the producer, then this number should be 0. And for the most part, many of them are 0. These are injectors. We interpret this as Law's injection, but there are several cases in here in which fluid is going into the ejector but not showing up as the producer. I think you need to shut those wells in. Right. More about this later. Time constant. More about this later, too. As I said, most of the time we do not have bottom hole pressure data, but when we have it, it is wonderful. Watch this. Remember the equation. And we've been neglecting this term right here. And now for the next few slides, we have this term. We have this data. Remember what the parameters were. Never forget Folkert Braun's famous quote, "Pressure is a reservoir engineer's best friend." This is a North Sea case. Now, there's not many wells here, only about 6 or 8 wells or so. So this is just a plot of the rates. There are 2 injectors over here. These are the lines. Very noisy, very noisy. And then there are 3 producers, which are here. And this noisiness in the injector, of course, is translated into noisiness in the producer, and that's what we're trying to take advantage of. One of the reasons for the noisiness is that the wells were periodically shut in. So here's the 2 injectors, and here's the shut-in times on the producers. A shut-in on an injector is a good thing because that makes the inlet signal very rich. A shut-in on a producer is a bit of a problem. So we still have issues with that. Maybe that's something you might do some thinking about as you work forward. So here are the 4 producers. This is the green is the production rate, the red is the bottom hole pressure. Here's 1, 2, 3, 4. And you can see in every case when there's a shut-in, when the rate goes to 0, the pressure rises. It's just basically a shut-up build-up test. And there's lots of them. Lots of them. Lots of them. Lots of them. Some places where they appear to have controlled the pressure except for the periodic shut-ins. And I'll skip that one. We will run CRM with the bottom hole pressure with and without. So here's a match of the rate as a function of time without the bottom hole pressure. We do pretty well. Here's a plot of the predicted production rate here versus the actual production rate. And it still satisfies Lake's law, 0.74, but there are some characters to it here. But that character goes away when we add in the bottom hole pressure. It's an excellent match, 0.93. You can hardly get better than that if you were making it up. And one of the things that comes when you have bottom hole pressure is that you can revert yourself back to the original petroleum engineering space. In other words, you no longer have to talk about time constants. You talk about productivity indexes, and here they are. This is the productivity index of the 4 wells, and you can see this well has a low productivity index, but it's pretty constant. And these 2 wells are periodically declining in productivity index. In other words, it's being damaged as you produce. So I'll stop and ask if you have questions. Questions? Yes.
Parameters you use perturbing for your history match?
We're changing the gains, and we're changing the tiles. Since we have pressures, we can take the tiles and decompose it into a pore volume and to a productivity index. Other questions? I'm going to do a little skipping in the interest of time. We'll skip Cranfield. Just one more to show you the degree of matches. Can't skip this one. This is the one that was actually developed by 2 other UT chemical engineering students. It's called the integrated capacitance-resistance model. I apologize, but not too much for the equations. And so here's the original equation up here, and it occurred to me one fine day that I don't really have to solve it as a differential equation. I can just basically integrate it straight out. So I can integrate that term and get that. That becomes this. I can integrate that term here and get the cumulative production, which is here. I can integrate that term with the cumulative water injection, which is here. And I can integrate that term right here, which is the difference in pressure. So I've now got a single equation that's not a differential equation. It's got 3 unknowns, 1, 2, 3 over here, but it is a linear equation. And the advantage of a linear equation, of course, is that there's an enormous body of literature on fitting data with linear equations, not the least of which is that you can assign uncertainties to the parameters. So the 2 students did this. One of the nice things about it is that you can apply this to primary recovery cases. Folks, we've strayed a long ways from our starting point. We started off with legacy assets where we had water floods and no bottom hole pressures. And now we're doing modern assets that there is no injection, but we have only bottom hole pressures. This allows you to, with fits, to calculate the drainage volume. I just want to call your attention to these plots here, which show the productivity indexes again. There's only 3 wells in this field, and to compare that drainage volume there with the geologic estimate, 31 to 59 million cubic meters. So if you give me pressures, I can associate the volume drained to each one. So I'm going to skip a little bit. It's okay? Yeah, because we are running late. Because I did want to hit this, since I think many of you are interested in optimization. Well, it isn't much of a trick. It's basically just doing what we just did. Once we got the gains and the time constants, and when we fit the oil model, which I skipped over to the oil production date, fix those parameters. So we say that the time constants don't change, the gains don't change, and the parameters in the oil model don't change. I get a lot of pushback on that too, but that's exactly what we do with conditional simulation. Once we get a history map, we say those permeabilities never change. That's what we're doing here too. So back to the Southwest Leveling case. Going forward, fixed gains, fixed times constants. See the summary there. And we will now adjust the injection rates so that they produce the maximum oil recovery or whatever in the future. Okay, this is true optimization. Individual injection rates by time. By time. Now, before you get carried away on this, let me tell you that we've never actually done this in the field. These are all calculated results. And I frankly think this one is a little too optimistic. But you'll see at the top up there is the injection rate. And we always fix the total injection rate of the feature to be constant. That means the individual rates can vary, but the total injection is constant. And that's pretty realistic because a lot of West Texas operators are running short of water. The bottom plot shows the oil decline rate And here's where we start the optimization, and here's the extrapolation that would have occurred had we done nothing. And here's what this is. Just playing with the well rates. No chemicals, no CO2, no new wells, no conversion of wells, just playing with the well rates. Now that's nice, but really the best thing that comes from it is the operational decisions that come from it. So what we're showing here is the injectors, percentage of injection share for each injector. That's the historic share, blue, and the predicted share. So if you see a blue curve without a red curve, that refers to an injector that needs to be shut in. If you see a red curve and a blue curve, that refers to an injector that needs to be bumped up. What could be cheaper than changing the rates? It's just turning a valve. You might be surprised how people can dig in their heels on this. But this is the operational choice. This is really more important than the fits. It's more important than the prediction forward, because it's telling you what to do, directly telling you what to do. Right? When we first started publicizing this, it was part of a research program. And we got a lot of people joining the research program, and it became very apparent that most of them really didn't care about the research. They were interested in doing this on their field. And so we started a little company, just a 2-person company whose only function is to run this on the field. So let me show you some sample results from that. There's no field name on it because we can't divulge it. And there's several optimizations. Here's millions of dollars. Here's the NPV that the field would have if you continue operating. Here's the NPV that it would have if you did the optimization. From a little more than 260 million to a little more than 300 million. Now, in the grand scheme of things, that's not a lot, but it's still $30 to $20 million for changing the valves. Okay. Here's the incremental barrels produced. In this case over here, we actually produce less barrels. Now, this is injection, excuse me. We inject less than we did before, and we produce more. Oil. This is another case. So we bump up the NPV from 360 to 420. Less water, and oftentimes the biggest benefit is using less water. Here's the increase in oil production from about 25 to 27, about 2 million barrels. These are not like something that would make your heart beat faster compared to an EOR project, but it's just changing the valves. Finally, my favorite case. Here's the case where the NPV hardly changed at all. The injection volume didn't change at all, and this hardly changed at all. In other words, it didn't work here. Okay? The optimization didn't lead to anything that improves the situation. This is real important, because not even the best technology doesn't work sometimes. So, question?
Have you tried to look at the geology of that field and determine if there's something going on that is making it less susceptible to the optimization?
I'd love to do that. That's the operator's task. We don't want to use any geology. But we do get asked all the time, is there some way to put geology into the model? And I'm sure it would help. I just don't know what to do, how to do it. Other questions? Okay, summary. It's supposed to be a 40-minute talk. It's 50 minutes. What we've learned. The whole procedure is done in a spreadsheet. So we get the data from an operator in a spreadsheet, put it in our form in a spreadsheet, push the button, there's results come back in the spreadsheet. And GAMS is not in a spreadsheet, so what it does is it spits the information over to the GAMS program, does the optimization, and it comes back. But it's an enormous advantage to be able to do things only in a spreadsheet. How many people here use spreadsheets in your work? Okay, it's not MATLAB, it's a spreadsheet. Second, the geologic model is output, not the input. At this point, I usually get a group of geologists that sort of huddle in the corner to prepare the tar and feathers. Always get great recoverable matches. The GAMS is wonderful. The solver is wonderful. The model is simple enough so that you can get really, really good matches. Often get non-intuitive, controversial results. See, this is a challenge to what you think you know about what's going on in the reservoir. Matches other sources reasonably. Now, I had another 20 minutes of this talk that showed the comparison between this and seismic, this and tracer data, this on geologic structure, and things like that. And it matches these other data sources reasonably. Applications. Well, I don't know if I've got them all here or not, but they can be used for surveillance, used for characterizing the reservoir, determining drain volumes, and I skipped over the section about determining relative permeability. You can't determine relative permeability from processing the data. Balancing injection. The SP literature is full of papers that talk about how they've balanced injection in this field, and they've done it on the basis of the surface locations of the wells. This is really balancing injection on the basis of the geology. Identifying problem wells for further treatment. And last but not least, I give you the Gardner Hype curve. This is what happens to a technology when you introduce it into the literature. Here's the height, the visibility, here's the time. You go through a peak of inflated expectations. This is where I am, by the way. Followed by a trough of disillusionment, and then I expect it to show up on a plateau of productivity. In our business, it characteristically takes 11 to 15 years to get way too slow. Okay, now that's it for me. Any further questions? Yes.
You chose productivity index is for a steady state, and the model CRM is not a steady state. It's not a contradiction.
Are you talking about the PI formula?
Yes. For J index.
The J formula?
Yes.
Yeah,
J
that's for
formula.
semi-steady state, where the rates can change. But it actually is after the transient flow part has passed, and I do not understand why it works so well. I just know that it works. I just know that everybody uses that formula. I don't know. I understand with all these perturbations going on why this quasi-steady state formula works.
Is there any other formula that is not for a steady state?
I hope so. I've got a student working on this right now. There are analytic solutions to transient flow problems, including semi-steady state, which should be useful right now.
Okay.
Other questions? Yes.
So what do you think is happening downhole? Like why if you're decreasing the injection rate, why does that increase oil production?
What it does is it takes, we're not for usually decreasing injection rate, it's taking, the optimizer looks for a well pair that has a good connection, injector conducer, and also has a high oil cut. So then it increases this rate, it gives you any pair that doesn't have any connection, it ignores. Any pair that has no oil cut, it ignores too. I haven't looked at it in details, but the time we did look at it, that is what happened. Yes.
In order to apply all these models I mean, you showed that one optimization curve where you could just run all those wells until, I guess, the reservoir dies out.
Until you get an economic one.
Yeah, but do you need varying data almost as an input into this in order to see? Okay.
Yeah, not to worry. It's always varying. Not to worry. Another question? Yeah.
For reservoir, I guess like acquisition teams looking out to, make acquisitions of say legacy assets or even current assets, do you see them purchasing, we're trying to build models similar to this and replacing the old Ares models that they've been using to try to find, I guess find things that they can buy at lower values, knowing that they can make an extra 40, 50, 60
I'll put that on the list. Is that okay? Because as far as I understand it, Ares is just an extrapolation of current production. This is extrapolation plus a recommendation.
I know that's what we're doing. We're using Ares. We're kind of just looking at it and saying, but we've been looking at your papers now.
We should talk, because I think we can probably run a case a day and probably give you a month on the numbers. As long as you're willing to do what it says. I mean, you'll have to shut in some wells, right? You'll have to increase some others. One of the very practical extensions here is that injection wells usually do not exist in a vacuum. They usually are linked up through batteries or collections of wells. So it's not so easy to change the rate of an injection well. But I'm sure we could run this with groups of injection rates to say what the battery rate should be. Other questions?
Over here.
Yeah. What?
How long does it take to do the study on a, say, a 50 well field?
Yeah.
Just now.
It just takes some playing around. Optimization programs always have a little common duty, but it's usually
And can this also, can it be used for like CO2 floods as well?
Surprisingly enough, it does work, because we're working at reservoir volumes, which doesn't matter what the fluid is as long as you have the right formation volume. So we've done CO2 floods. I don't know exactly why it works. It's a little bit why her question over there about why semi-steady state works. But we get good matches in there. They seem to be. Other questions? You know what the difference between an undergraduate and a graduate class is? If you go into an undergraduate class and you say good morning, they say good morning. If you go into a graduate class and say good morning, they write it down. Thank you very much. You're both